Good morning and welcome to this presentation on Bluetooth LE audio, where we will cover both the specifications and the Zephyr implementation of them. I am Asbjørn Sæbø at Nordic Semiconductor. I participate in the LE audio specification work, and I also contribute to the Zephyr host code. My co-author, Emil Gydesen, also at Nordic, is the main developer for the Zephyr LE audio host implementation. So, why is LE audio important to Zephyr? Well, firstly, LE audio is coming right now. Most of the specifications are done, and the last specifications for a complete system are expected to be completed now in June. And LE audio has the potential to have a significant impact. It will be used by a large number of devices, and it will significantly increase the number of Bluetooth-enabled devices sold. The forecasts are that in a few years, several 100 million LE audio devices will be sold per year. And the indications are that a number of these devices will be running Zephyr as their operating system. Add to this that Zephyr already has large parts of an LE audio implementation in place, and we can see that a new and important range of audio use cases and products is coming, and Zephyr is well placed to play a role in this. In this presentation, I'll go through three topics. The first is, what is LE audio, the features and the use cases? The second part is a brief overview of the specifications. And the third part is an overview of the Zephyr implementation with an example on how to use LE audio in Zephyr. So, let us have a look at the main features and use cases of LE audio. A major feature is the flexible topology. LE audio can do point-to-point, it can do point-to-multipoint, and it can do point-to-many. The point-to-point is a connected mode, and it can be unidirectional or bidirectional. This could be audio from a phone to a headset with microphone for teleconferencing, or it could be unidirectional audio from a doorbell to a set of hearing aids. The synchronized point-to-multipoint is an important feature. This allows what we call true wireless stereo, audio to two separate devices. So this could, for instance, be TV sound to two earbuds. And this is the first standardized Bluetooth solution for doing this. LE audios can also do point-to-many. This is an unconnected mode. It's unidirectional. This can be used for broadcasting audio of various kinds. One possible use case is to replace the telecoil. It can also be used for various forms of audio sharing. Some possible use cases are to transmit the sound in a lecture hall from the speaker to the audience, or to get gate information at airports, or to get hold of the audio from the TV screens in pubs, where it's often difficult to hear the sound. They are often muted. The streaming from one to several devices is fully synchronous. You can have several simultaneous streams to separate or independent devices. The number of these devices is in practice limited by airtime capacity. There is only so much airtime to go around for the transmissions. But the important point is that all receivers will have the same latency. They will be synchronized. And this synchronization is accurate enough for binaural audio. We are talking about in the order of some microseconds, so that it will give a good and stable stereo picture. And this synchronization will also happen between equipment of different brands. The topology of LE audio is also designed to be very dynamic and to have the hearing device in the center. There will be many sources and many sinks, and these devices will announce their existence and their availability for audio using advertising. The hearing device will be able to pick from all these devices. It will dynamically set up and tear down connections as needed. It will be able to discover new sources. It will be able to be connected to several sources or to switch between sources. And there is also a mechanism for automatic prioritization based on the context types of the available audio. LE audio also comes with a new codec, the LC3, the Low Complexity Communications Codec. Compared to the previous codec, the SBC, the LC3 has higher quality and lower bitrate. It's a single-channel codec. It can run on multiple sampling frequencies, on several different bit depths, and 2 different frame lengths, and it can encode to a quite large range of bit rates. The figure shows the subjective score of the LC3 codec, and as can be seen, it gives high scores even at low bit rates. LE audio has been 8 years in the making and consists of a number of specifications and specification parts. So let's have a look at those. Some major parts of LE audio came with the Bluetooth Core Specification 5.2. Here we got the isochronous channels. These are often called ISO channels. And isochronous means with the same time or the same clock, basically going at the same rate. And the ISO channels are the data transport for LE audio. They transport only data, not control information. There is connected ISO, which goes between 2 devices and can have one-way or two-way streams. And there is broadcast ISO, which is one-way, one-to-many. Common to both the connected ISO and the broadcast ISO is that there is only a limited number of tries for each data packet. If they are not transmitted correctly within that time, the stream continues with new data. In the 5.2 specification, we also got the ISO adaptation layer, which is basically segmentation and reassembly for ISO data the ability to restructure data for transmission. And we got the extended ATT, which gives multiple ATT bearers, so that one can do parallel ATT procedures. There is a specification for the LC3 codec, of course. And there is a number of specifications for the control plane and for the use cases. The control data for LE audio are transported using a series of GATT client and GATT servers. And this is called the generic audio framework. And then there is higher level profiles and services for the various use cases. Here are the profiles and services for audio control and for the various use cases. The lower part is the generic audio framework. The upper part is the use case profiles. At the lower right, we have the audio stream control. This is the basic audio profile and the associated services, the published audio capability service, the audio stream control service, and the broadcast scan service. So these are the profiles and the services that is used to set up the actual audio streams. To the left of that is the coordinated set identification, which is used to define sets of devices that belong together. For instance, a set of two earbuds. There is also volume control and microphone control, with the services for volume control, volume offset control, audio input control, and microphone control. For content control, there is the call control profile with the telephone bearer service for all kinds of calls, telephone calls, Skype calls, team calls, whatever. And there is the media control profile and service for controlling various forms of media players. And they use the object transfer service and profile. On top of this is the common audio profile, which defines procedures for setting up streams for sets of devices and controlling sets of devices. Above this, we find the use case profiles. There is the telephony and media audio profile to the left and the public broadcast TV profile to the right. In the middle is an interesting one. That is the hearing access profile and service. With LE audio, there is no standardized solution for transmitting audio to hearing aids, which is a very welcome thing for those dependent upon such devices. The Zephyr LE audio implementation has been developed over several years by a set of cooperating partners. I'd like to take the opportunity to give some kudos to the companies that have contributed. There's Nordic, Demant, Intel, Bose, and a few others. Since the specifications were not public at the time, the development started in the private repository. But now all is upstream or in PRs to upstream, and development is now happening in the open with PRs to the main branch. On the host side, we have mostly been building upwards. It's mostly in place up until CAP and HAS, which is what we are working on now. TMAP and the public broadcasting profile are next on the list. The controller is roughly 3/4 in place. The connected ISO is currently missing, but it is in the works, so it will come. There is too much code to go through it all, so I'll take an application developer viewpoint here, focusing on the host code and in particular the stream control, which is the core of the matter. So I'm going to have a look at the host profile and service code, where it is and what it is, and I'll show an example of what is done to transmit and receive unicast audio using an abstraction layer over the basic audio profile and services and the ISO. And you should note that these things may still change, both the naming and the code itself. So we start with the host code, the control profiles and service. The code is where it's expected to be under Bluetooth audio. We can have a look at the header files. Which you can see here. Here, for instance, we see the audio.h, which is the main header file for the abstraction for the basic audio profile and streaming, together with the capabilities. We can see the AICS.h header file, which is the audio input control service. There is the CSIS coordinated set. There is the HAS hearing assistant service. There is the LC3 header file, media control header file, and so on. If we continue to the modules themselves, we see the source code, similar. Code for AICS, codes for broadcast assistant, code for broadcast sync, code for broadcast source, code for a coordinated set client, code for an endpoint, this is an internal header file, code for hearing assistant service, code for media control client, and so on. There is around 28,000 lines of code here in this module directory. In addition, we have BabelSim tests, which tests the main functionality. We have shell applications, there are samples, there is a bit of documentation. And Zephyr also has an LC3 implementation. This is the LC3 implementation from the Android open source project. And it's integrated into the Zephyr samples now. So that was a very brief overview of the host code. Let us walk through an example of transmitting audio. In this example, we'll use the stream interface, which is contained in the audio.h header file. This wraps the stream control profile and services, the basic audio profile, the published audio capabilities service, the audio stream control service, and it also wraps the interface to the ISO channels, the connected isochronous group and the connected isochronous streams. And this is a unicast sample where we have two roles. The unicast client, which will typically be a PC or a phone, and the unicast server, which will typically be a headset, or a headset with microphone, or a microphone. And what is not shown here is the announcement that the devices send out to show that they are available for audio. So the first thing that happens is that both the client and the server need to register the stream callbacks. The server will in addition have to register a set of capabilities, basically saying what it supports, what endpoints it has, what direction the endpoints has, what codec it supports, what codec parameters, and so on. And the server will also have to register some server callbacks. With this done, the devices can connect. This is a normal ACL connection. And for audio streaming to work, there is a need for a larger ATT MTU than the default, but this is now done automatically in the stack. So this is how the setup and connection is done. The next phase is discovery and configuration. So the first thing here is that the client needs to discover what the server can do. So it does an BT audio discover, which will basically find the information supplied by the published audio capability service on the server. And this is returned in the discover sync callback, assuming for now that we are discovering a sync. And the arrow in front indicates that this is a callback. Given the information we have now found, the client can proceed to configure the stream. So this is basically telling the server which codec and codec parameter the client wants to use. So it sends this over, which results on the config callback on the server, and eventually a configured callback on the client itself. It's also possible to do a reconfiguration here. Next step is to set the quality of service parameters and enabling the stream. Quality of service parameters, that is things like the number of retransmissions allowed. So first the client does a group create, which takes a set of streams. And the streams can be to or from more than one device. It will then do an audio stream QoS call to set the quality of service parameters for the whole group. So all streams in the group have the same quality of service parameters. So this results in a callback on the server and a QoS set callback on the client again. After which the client can do the audio stream enable, which basically is telling the server that the client is committed to these settings. So again, callback on both sides. At this point, we are ready to start the streaming. So the client does a stream start call, the server gets a start callback, and the client gets a started callback. After this, the client must at regular intervals call the BT audio stream send with data to be sent to the server. Server will receive the audio data in the receive callback, and the client gets the sent callback. And when there is no longer a need to stream any more data, the client will stop the stream. So after the stream has been stopped, the client will disable the stream, which basically disconnects the isochronous streams. And it will do a release to tell the server that we are done with this stream endpoint. And the server may then put its endpoints into the idle or the configured state. And we are basically done with the streaming. So, this was a brief overview into the LE Audio. I hope you found it informative. We are available for questions in the both here and in the Discord channel of the Zephyr project. Thank you.